So the upshot of this is that if I look at just binaries from first generation, there's a hard cutoff at about 80 solar masses, so that's 40 plus 40. But if I look back at this, right, there's suddenly a huge number of objects in that second generation above 80 solar masses. And this, we think, is essentially filling what's called the pulsational parent stability gap. And if I ask the question, how many of these binaries do I expect to have masses in that gap, whether I define it as above 40 solar masses or 55 solar masses, I can make very good predictions for the detected distribution from star clusters. If I define the lower edge of the gap as 40 solar masses, and every black hole from a star is born with 0 spin, then about 12% of all binaries will have, from a star cluster, will have a mass in that gap. If I'm a little more conservative about the mass gap, then it's about 7% of all detected binaries. And at that point, I'm out of time, so I'm just going to go ahead and cut myself off and see if anybody has any questions.
Thank you, Carl. So, question for Carl?
Can you tell us about the bet that you had, and what were the parties, and what was the...
Right. So this was a bet that started a couple years ago with a sort of professional frenemy of mine, Chris Belchinski. Basically, the idea was that you can't really form these very heavy black holes outside of star clusters. They have to be formed, or you pretty much have to repeatedly merge objects in order to populate this mass gap. That's not, there are wiggle ways around that. You can accrete gas, you can start to futz with the gap itself, but for the most part, if you see something that's like 80 plus 80, that probably came from a star cluster. Chris is not very copacetic to other ways to form binary black holes, and he works on binary stellar evolution. And so essentially we started a bet that said within the first 100 LIGO detections, LIGO will see something with a single mass greater than 55 solar masses, which is actually why this particular line is in the paper. There's not really a good reason to have 55 solar masses there. It was just an extra line I added to annoy Chris. Which was a good reason to do science. But essentially the bet was that it was myself and Shirav Chatterjee, who's now at the Tata Institute in India, versus Chris Belchinski and Dan Holtz. And we've since added Fred Razio, who's my PhD supervisor, and Stan Woosley, who's the guy that does a ton of the work on pulsational parent stability. Essentially, if LIGO detects something in the mass gap within the first 100 detections, I get a $100 bottle of wine each from Chris, Dan, and Stan. I don't know what wine. I don't, frankly, know wine well enough to know if I'm getting good shit or not, but that's a different problem.
We're pretty close to getting it.
So I've been told. I think that's going to depend on the... There are rumors, by the way, that LIGO has detected something fairly heavy in the mass gap, with a total mass of around 160. I don't know. I'm just looking at Shenyu, who's now glaring at me.
Where did you get a number?
It's circulating.
I'm not going to tell you. I don't want to get people in trouble. I think that's going to depend. I'm interested to see what that number ends up being, though, because that's, I think, the early parameter estimation before they've done some of the Bayesian modeling stuff. And if they want to be really good bona fide Bayesians, what they should do for the parameter estimation is apply the prior on the masses from 01 and 02, which is going to be weird, because there the largest mass was about 50 solar masses, and what that's going to look like at the end, I don't really know. But somebody will have to, lock Will Farr in a dark room somewhere and start asking questions. But
So I probably missed it. So how are we gonna tell the difference between all these, say, 4 scenario you're showing here? Like, what do you need for us to tell?
So I think the really obvious thing is something in the mass gap, because LIGO measures mass really well. So that is, I think, the sort of telltale sort of way to do this. The other way to do this, which is what, for instance, people like DeVita and DeVita. God's sakes, just go back and do this the old-fashioned way. People like DeVita Gerosa and Maya Fishbach were looking at. Come back here, you. Too far. Is that you can essentially look at different. You can essentially look at different mass distributions, even without the pulsational parent stability gap, and different spin distributions, and you can start to say, all right, if I have multiple channels all contributing to the LIGO rate, I can essentially phrase this as a Bayesian hierarchical modeling problem, and start to use individual detections to contrast the individual contribution.
And how many, roughly, how many number of
So
detections?
this paper claims that you need about 100 detections, I think. No, sorry, I take that back. This figure is showing what you can get, the sort of contour regions on what you can get with 100 detections by LIGO. So this is showing this plot's a little peculiar, but essentially this corner of the triangle is all black holes are first generation black holes. This corner is first generation plus second generation, and this corner is second generation plus second generation.
Is that making any sense? So you're saying all my events come from second plus second generation, but they never were allowed to become second generation in the first place?
No, it doesn't really make physical sense. But essentially what they're doing is saying, well, I could cook up a universe where that happens. It would be weird. I mean, you can imagine all the first... Yeah, if all the first generation black holes merge like at Z of 10, then you could imagine doing it. It would be really artificial, but
It's possible.
yeah, I could do it if I really needed to.
My guess is that their estimate is that this is the contribution of the three channels, 60, 10, and 30%, and they see whether they can...
Exactly. So this is the
That's
injection. This is actually one of their sort of mock. This was essentially a mock way of pulling these numbers out. So this was the true universe that they synthesized, where 60% are 1g plus 1g, 10% are 1g plus 2g, and 30% are 2g plus 2g. And then they said, after 100 detections, how well can we map out this parameter space? And so this is just showing the true value, and then these right here are showing the credible regions. Yeah. No, this was a cool paper. The Fishbach paper, which came out around the same time, does this from a different perspective, but is also very cool.
Yeah, last question.
Yeah, so from the previous plot, maybe I misunderstood, but it looked like if you cranked up chi effective, that especially the massive black hole, more massive black holes from like the second generations kind of decreased. Whereas for me, intuitively, I would say if you crank up the chi effective, the first black holes you kick out are actually lower mass ones.
So it's independent of mass, essentially the radiation recoil kicks. So GR is essentially mass independent, and it actually, the only thing that the recoil kicks depend on is the mass ratio and the spins.
Yeah, but isn't eventually the velocity of the, okay, so the velocity is also not dependent on, like it's not,
Yeah, so the velocity is independent of the total mass. It just depends on mass ratio and the spins. So that's, people were writing these papers well before we were talking about LIGO black holes. They were actually writing these in like the mid-2000s, talking about, for instance, what happens when you merge two supermassive black holes. Like, does it stay in the galaxy? Because 5,000 kilometers a second, right? That's above the escape speed of most galaxies. So you merge that, it's going out. That, of course, depends on whether you think supermassive black holes have large spins or small spins, and that has to do with their merger history. It's all very cool stuff. But yeah, it's essentially, once I dial up the spins, I'm subtracting all of the masses essentially equally, or sorry, lowering the retention fraction of all masses equally. The only thing that changes is whether or not that happens early on when the cluster still has much more mass and a greater escape speed, or if it happens later on.
Okay, so let's thank both our speakers again.
Thank you. I've been here for 2 hours.
Thank you so much.
We don't need to give anything.
I've been here for 2 hours. I'll get the
Okay. In the event of very the future,
I didn't know they were decreasing. I wanted to write this paper because
We're going to get things up.
Sounds good.
Yeah.
The TDS.
Yeah, like extreme. One is mine.
What's the last
It's real, it's mine.
Yeah.
But it's not in the right?
Yeah.
No, it's not in the but it's the
Yeah,
high
that
mass.
was, I'm less, I've seen the LIGO people give talks on that. I'm not really, I can't really say, should I ask a question? You?
Well,
Is
also,
not the
survival
IS.
of the IS
actually.
outlier should we pay attention to?
do it in the general case,
So
unfortunately.
some of them.
No,
and
but this
they're
one,
still-
the one that is on the side.
The one that they claim to spin at 0.9. By the way, I reweighted those posteriors so they were using the same distribution.
Yeah, no, this
Oh,
is
so
just a
that's
huge
the
array.
prior-
Yeah, it's after I
Full of
invented
numbers,
it,
except
It
for
would be
the-
nice if the LIGO team would put
Because
like
I need to
a
slow
table
down
with
look,
the
there's a lot
reliability
here.
that they assign to these different events.
Up here,
We're working
these are
on
all
that.
Oh, you're
I
working
was
on
gonna say, aren't you and Alba writing
Yeah.
that paper?
The rigidity gives liability what they think it is, which is smallest way.
Cool.
Yeah.
I mean, all of these things are based on.
It's nice to be able to provide.
It's still based on the certain.
Well, also, I'm gonna probably try it.
Yeah. Well, it's also like you do the false alarm rate based on how often you get false alarms for your template bank, and because they're using much smaller template banks, it changes the false alarm calculation for LIGO. I'm not really an expert on it.
Another location.
I'm speaking from behalf with my understanding as outsiders. They have at
Papa
least
Dimitri
4 or 5
still
different pipelines. We don't
the
usually see 2 of
McPhee
those.
coordinator?
Those don't agree.
He never was.
Partly see-
Oh wait, it's who is
and
it?
part of it is giving us a sensible answer, but it's also politics, which pipeline do you put forward?
And some of them, and I didn't appreciate this till a couple of weeks ago, they're not actually the real FARs, they're just lower limits that, for instance, pi CBC goes. So a lot of the like 03 events have FARs of 1 every 17 years. That actually just turns out to be the lower limit that that particular pipeline spits out when it's like in the weeds.
Yeah, that's true, but it's not, what we can predict is online and offline, we typically get better far for the event.
Should we trust LIGO more than IAS? That's the question.
That's two different analysis.
Yeah, I think the IS thing, because talking to them, they are so confident with that event.
They do have, one thing I really like about IS, they're most confident